Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is CSA A23.3 2019 Concrete Building Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Choa will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, we will be working with the structure that you see over here on the right-hand side. So we'll begin in our main program, RFEM 6, where we will review the model as well as the loading. Then we'll move on to utilize the concrete design add-on for our member and surface reinforcement input data. We'll also be taking advantage of the new add-on within RFEM 6 called the building model. So this allows us to define building-specific elements such as diaphragms, spandrels, and shear walls. And finally, throughout the presentation, we will be running both the analysis and design and taking a look at the results in more detail. So we'll immediately begin within our main program, RFEM 6 here. As you can see, I've taken the liberty to already model our concrete structure. But if we visit our base data by right-clicking on the model name, when you begin a new file, you will give it a model name. The type of model will be in a 3D environment, for example, today. And under the second tab are our various add-ons. So RFEM is responsible for the full analysis of our structure. But if we wanted to take this a step further, and in particular today, to carry out the concrete design according to the CSA standard, then we would need to activate here that concrete design add-on. Now, under this third tab, you can see here that we will generate the load combinations automatically according to the NBC that is selected here from our dropdown, but many other international standards are also available. We also will be utilizing the 2020 standard. As far as the concrete design, we will be carrying out the design according to the CSA A23.3, the 2019, but if you do have access to the concrete design add-on, you will also be able to run your design according to the ACI, the Eurocode, or other international standards offered. So once this information is input, we can go ahead and jump back into the main program RFEM here to review the model input data. And we'll begin with our materials. So over on the left-hand side, you can see that the concrete compressive strength that I'll be utilizing for all of our elements today will be 40 MPa. If I double click on this material, I wanted to point out that the material type is set to concrete. And when we do this, we have an additional tab here to specify the creep and shrinkage properties of the material as well. So this will come into play a little bit later on with the long-term deflection. Now for our example today, I'm going to leave these options turned off, but just keep this in mind for those specific concrete materials. I also have here defined the reinforcing steel material, 500R. This will come into play also later on as well with our reinforcement input data for our elements. So in addition to the materials, we also have our cross sections. You can see that I actually only have one cross section defined for our members, which are the columns kind of running up through the center here of our structure. And double clicking on these particular members, you can see that the member type is set to beam. So this would be any standard beam or column element. What also may be common with concrete design is the member type rib. So we can actually place a beam element below the depth of the slab here, integrate the internal forces to design this as a T-beam. Now, I won't be utilizing this type of member in today's example, but in the previously recorded webinar for ACI 318 design, I do go more into depth with the member type rib as well as the design, so you can refer to it there. For today, just using the standard beam type for our columns. We also have here the cross section and the material that that are assigned to the member. You can see this is just a standard 300 millimeter by 300 millimeter with that same concrete compressive strength assigned as the material. As far as our surfaces, so we have two different thicknesses assigned to these surface elements. For our walls, they are all utilizing 150 millimeter thick definition type here. And then as far as our floor or our slab elements, these are going to be slightly thicker at 250 millimeters. With the modeling of our surfaces, you'll notice that all of these segments here for spandrels and shear walls are modeled as individual surface elements. This is a little bit better output when it comes to the building model that we'll visit later today in our example, but this is in contrast to modeling one continuous surface here and inputting in standard openings as you see up here in our toolbar. So again, just a little bit better behavior when we're talking about the building model add-on, but we are working in the next several weeks to optimize this so that the building model can also just handle standard surfaces with standard openings. But for example, today, again, just notice that all of these are individual surface elements that are modeled around the openings themselves. And finally, you will see down here at the bottom our supports defined. So just a standard pin type application here at the bottom of our 2D surfaces with a line support. So this pin support will be applied at every FE mesh element at the base of these walls. We also have a single nodal support here at the base of our column. So now that we have reviewed the general information here for our model, I want to get into the loading. So we'll go ahead and access here our load cases and combinations dialog box. As you can see under the base data, we have the same information that we defined here within the dialog box that we previously saw, where we're going to generate those load combinations automatically according to the NBC 2020. Now, when this checkbox is checked, we will generate those load combinations automatically. Now, alternatively, you certainly can uncheck this option here to manually generate the load combinations instead. Then we move on to the load cases. So for the example today, three very simple load cases. We have dead load with the self-weight active over here on the right, live load, and wind load. And you'll also see that the action category is defined for each one of these load cases based on the NBC standard. This tells the program how to combine these load cases in the load combinations and which load factors to also apply. Jumping now to the design situations tab, you can see here that two design situations are automatically generated based on the NBC, and design situations are always needed when we carry out the design within these additional add-ons. So because we've activated the concrete design, you'll notice that the design situations are both listed here for the concrete design and turned on. This will make more sense when we get into this actual add-on a little later on. A design situation is nothing more than grouping together the factor load combinations here according to the NBC standard for this first design situation. And we can review this data directly from the NBC standard with this info button. The unfactored load combinations are part of this second design situation. Again, we can reference the code here. All load combinations will be carried out according to a second order analysis. And finally, we jump to our load combinations tab here. You can see the individual load combinations listed out, and our factor load combinations in red belong to that first design situation, and our unfactored load combinations here belong to the second serviceability design situation. Now, before we move back to the RFEM model, I want to quickly explain how we can take into consideration the I crack factor requirements from the CSA standard, and in particular from clause 10.14.1.2. This is a requirement from the standard, as mentioned, that we apply this crack factor to the stiffness of our elements within our concrete model. The problem is that when we draw this model, this is not automatically taken into consideration. So rather, we need to give that definition type here directly under the load cases and combinations. So we'll begin back here under the load cases where we have the structure modification checkbox. What I'm going to do is to create a new definition type here for both our members and our surfaces. Now we get 2 additional tabs up here at the top. So you'll notice under the member modification, I want to create a new definition type here. And we have an additional drop-down box where we can directly select the CSA A23.3. And with this, we're going to refer directly to table 10.14.1.2. And we have 2 different component types, columns and beams. Well, for today's example, we only have columns available in the model. So the I crack factor directly from the CSA standard, as you can see here for bending stiffness, will be applied to those members. So once we create the definition type, I do need to graphically select the members here that I would like to apply these to. So I'm just going to choose the 4 column elements here, and you can see the numbers 1 through 4 are now populated within this table. We do the exact same thing with our surfaces tab. I use my drop-down box here to create a new stiffness modification. I utilize my drop-down box here to yet again select the CSA standard. And under the component types, we have 3 different options, and we'll begin with the walls uncracked. So we have the relevant I crack factor that will be applied to our 2D surfaces for our wall elements in bending and torsion. I click OK, and now I need to graphically select the wall elements. I could individually select these or use my selection box graphically, but another easy method is to go ahead and take advantage of the navigator view options here, where you can see that we can select various elements. And we'll begin with our surfaces, where I can select all surfaces graphically by their thickness. So I can go ahead and select all surfaces that are 150 millimeters thick, which will essentially be all of my wall elements. I graphically select them, I click OK, and now those values are input into this table. Now we lastly need to create one more stiffness modification. We're going to use our drop-down for the CSA standard to select flat plates and flat slabs. The I crack factor is updated from the code to 0.25. I click OK, and now I need to graphically select the members that this will be applied to. So I'm going to modify my views here to the surfaces that are 250 millimeters thick, which are all of my floor slabs. I select those, I click OK, and now this information is complete. So now that we have this structure modification definition, we want to apply this to the additional load cases here. So I can select both with my shift key and to simply activate this modification yet again. But it's not enough to only apply it to the load cases. We also need to apply it to our load combinations. The easiest way to do this is to go to the design situations themselves. And I had mentioned how we're automatically running a second order analysis with the combination wizard settings down here at the bottom. Well, if we go into the detail settings for this, we also have that exact same checkbox that we can turn on here for the design situation, which will in turn affect the load combinations. But I'd really like to apply this I crack factor only to my factored load combinations for the ultimate limit state. For my serviceability, I really don't want to apply the I crack factors. Instead, what we refer to for topics like deflections under serviceability is the effective moment of inertia. And this is called out in clause 9823 within the CSA standard. Well, when you do the design within the concrete design add-on, the effective moment of inertia will automatically be calculated. So I want to go ahead and turn off the I crack factors for my unfactored load combinations. A very easy way to do this is to make a copy of my existing definition type and to simply turn that off with the checkbox option. So now with my factored load combinations, I leave this with my first definition type, but for my unfactored, I'm going to use my drop-down box to select that third definition type. If we jump to the load combinations, we now see our factored load combinations here with the structure modification turned on, and our unfactored load combinations will have this option turned off. Okay, so now that we are complete with the load cases, the load combinations, we've applied the I crack factor requirements from the code, I want to go back to the RFEM model here just to take a look at the display of our loads. So again, very simple application for today. For our dead load, you'll notice here that I just have simple surface loads applied at each floor level of 3 kilonewtons per meter squared. When we look at the live load, exact same concept, and you'll also see here that within RFEM 6, we can right click on these loads and decrease the size of them graphically with this slider tool. But I've essentially applied these live loads at the interior floors only. And finally, we also have here a wind load. So again, very basic loading application for today. We have 2 kilonewtons per meter squared in the global X direction, and then 1 kilonewton per meter squared as a suction force on the other side. And I recognize realistically, we'd probably have additional suction forces on the roof. We'd probably also want to consider these openings and apply them as line loads around the edges of our door and window openings. But for today, again, just sticking with this simple application. So now that we have our 3 load cases defined with the loading applied to this structure, we can jump down to any one of these load combinations and cycle through them to see the loads applied on the structure simultaneously, taking into consideration the load factors as well. All right, so now we have reviewed the loading. We are finally ready to input in the reinforcement for some of our elements specific to the CSA standard. And we will begin here with the reinforcement input of our columns. So I'll go ahead and hold down my control key to create a user-defined visibility for only these members. When I double click on all 4 of members, numbers 1 through 4, you'll notice that we have the design properties turned on here. This is just telling the program that not only do we want to carry out the analysis, but we want to take it a step further to actually design these in the concrete design add-on. And we have all the available tabs up here at the top. But notice when I uncheck these, all of these tabs actually disappear, just telling the program I only want to carry out the analysis with the concrete material, no reinforcement input. So what we, of course, will do is to input the reinforcement here, but assuming that we want to have the same reinforcement for all of these columns at all levels, I certainly could go into each individual member and input in this reinforcement, but alternatively, we can take advantage of what we call the member representative. So I'm going to access that same base data dialog box by right-clicking on the model name and jumping to the settings and options where I can turn on the member representatives checkbox. So what this is going to do is group together members that are really similar or identical in most ways, including materials, cross sections, the length. So now when I click OK, what you'll notice here is that I get a new option within my navigator called Member Representative. And this will group together these 4 identical members. Well, double clicking on the member representative to open up this dialog box, you can see that it includes members 1 through 4. And if I go into the edit members setting up here in the upper right corner, we're back into the same dialog box. I can turn on the design properties for those additional tabs here. But again, instead of individually inputting in this reinforcement, I'm going to click OK, and all of these exact same tabs will be available in the member representative. So this way, if I need to make any modifications to this reinforcement, I can do it through the member representative, which will in turn make those same changes to members 1 through 4. So we'll begin by working through these tabs up here at the top. The first one, the concrete effective lengths. This is only if you're going to carry out the moment magnification method. And because we are running a second order analysis, this is not required. Moment magnification is required for first order analysis. So essentially, we don't need to do anything within this particular tab, and we can leave it empty and move on to the next. We have here the concrete cover. So I'm going to specify 30 millimeters for my concrete cover for these columns. Under the shear reinforcement, this is where I'm going to specify my stirrups. So under the first dropdown, I choose the stirrup type, and I'm going to go ahead and choose the default first option here. The material is also set. So I already have this reinforcing material defined within the model. So I can just simply select it from my drop-down box. But if we did not have that reinforcing material available to us, we can click on the three dots here. This will bring up our material dialog box where we can access our material database. And utilizing the filters over on the left, we can filter to Canada. We can filter to the material type set to reinforcing steel, the CSA standard, and then we have these available reinforcement materials from the library directly. If we choose one of these reinforcement materials and we want to make some modifications, we can always choose the user-defined material option checkbox that will allow us to make modifications for a user-defined material. For today, again, we already have this 500R defined for my reinforcing steel, so we'll go ahead and utilize that. Now I want to select within this drop-down box the bar diameter. So we'll go ahead and select the number 10s here that are available with this first option. I specify the stirrup spacing such as 0.3 meters, and the number of bars will be set to 10. Now notice that the graphical display down here at the bottom will go ahead and update as I input in this information. Now you do not have to set the same uniform spacing and type of rebar across the entire member length. It might be very common for beams, for example, to have maybe more shear reinforcement at the member ends versus the middle. Well, we can simply create new definition types with this button here, and then we can specify exactly the start and the end of the shear reinforcement definition. But for today, for our column, leaving this as uniform spacing with those number 10 bars. Moving on to longitudinal reinforcement. So you can see by default, the program has set this to symmetrical, which might be more common for a beam. For a column, we want to choose the drop-down option, uniformly surrounding. Again, that 500R material will be selected here. We have a couple checkboxes to place the longitudinal reinforcement in the corners. This is really more applicable for T-beams. You can see that the reinforcement is already placed in the corners, so nothing to do with both of these checkboxes. We specify the number of bars, 4, and then we will also set the bar size within our dropdown. We're going to use those number 20 bars here as well. We can additionally specify the development length at the member start and the member end. I'm not going to do that for today, but this is something you can take advantage of, which we will check development lengths within the concrete design results as well. So now we have finished the reinforcement input. We jump now to the design configurations tab. And we have here two configurations. The first is the ultimate. So we go ahead and take a look at the default settings here. This is going to be information that is specific to the ultimate limit state design for our members. So you can see here all of the various options that we can turn on or off, or maybe we want to change values, or we want to choose a different method, whatever it may be. But also all of the code references for the most part are listed out here, so you'll easily be able to refer to the code to understand which setting belongs to which requirement here. We can also create additional configuration settings for different members. So currently we only have one definition type, but we can create a second definition type and assign it to different members and surfaces and so on. Same concept for serviceability. If we look at the detail settings here for the default for the SLS design, we're going to see information specific to serviceability, such as the crack control according to clause 10.6.1. We also will check deflections of the members. So you can see here the limiting deflection ratio for members that are supported at both ends versus a cantilever member. We also have here the calculation of time-dependent deflections. So the default option here is to refer to clause 9825, where we input in the duration of the load. And what this will simply do is to apply a deflection multiplier for the sustained loads to the instantaneous deflection. Well, this is certainly a very simple application here. Alternatively, if we want to take into consideration creep and shrinkage from those material properties that I mentioned at the beginning of this example, this is going to be certainly a more theoretical and exact approach for creep and shrinkage. For this, we're going to take the approach from the ACI 435 as well as the same approach that's followed within the Eurocode, as there really is no specific requirements from the CSA on this topic. Now for today, we'll just leave this as the simplified time-dependent factor here. So these are the various settings then with the serviceability and ultimate configuration settings that we'll utilize within that concrete design add-on. And finally, we have here the design supports and deflection. So when I don't do anything within this particular tab, the program is going to assume that this member is supported at the member start and the member end at exactly these points shown here. If we have a cantilever, then we certainly want to define a support at either the member start or the member end. But also specific to concrete, even if you do have a beam member, for example, that is supported at both ends, it's recommended here to create a new design support type. And the reason why is you'll see here the option for a concrete type support. Here we can specify the support width. And what this will do is to refer to the CSA clause 1132 that allows us, when we're talking about shear checks, to take the shear force at distance D away from the support edge. So the only way to take that into consideration then is to apply these design supports, and then we can take that, again, that shear force into consideration within the concrete design add-on. So maybe not so applicable here with our columns. We'll just go ahead and leave this as default, where all forces are taken directly at the member ends. So now that this information is input within our member representative, what you would typically see is the reinforcement shown here graphically. And I'll turn this into wireframe view. You can see here the longitudinal and the shear reinforcement shown. Okay, so now that we have the reinforcement for our concrete members, let us go ahead and cancel out this visibility and let us move on to the reinforcement of our slab. So I will begin with the slab that's shown here at the first floor, and we go ahead and double click on this element. You'll notice that we have the exact same checkbox available here for our 2D surface elements. This is telling the program yet again, not only to carry out the analysis, but also to perform the design within the concrete design add-on. So we will move through these tabs. We will start with the concrete cover, where we're going to increase the cover distance here to 40 millimeters at the slab top and the bottom. The concrete design properties. This is just simply telling the program that when I define my first longitudinal reinforcement, which direction should this be related to in terms of the surface's local axes. And the default here is the local x-axis. So once I get into the surface reinforcement here, what we can do is to create a new definition type. I'll create this new definition type here. And this dialog box pops up that initially has our first drop down here that's asking, where do we want to place this reinforcement on the surface? Do we want to apply it to the entire surface or just particular areas? So for our first definition, we want to apply this to the entire surface. The second dropdown is going to be our material, again, that 500R that we already have defined within the model. The reinforcement type can be a welded wire mesh, it can be a rebar, or if we are placing shear reinforcement for one-way shear design, we can specify stirrups. We will go ahead and utilize the rebar option for today. And in my dropdown, I can select the number 15 bars here, and my spacing is going to be at 0.15 meters. So this is the longitudinal reinforcement now in the local x-axis of my surface. But I'm likely interested in placing also transverse reinforcement in the local Y direction. Well, we can easily do this by checking on the checkbox here at the bottom. I select my bar diameter here with 15 m, and then my spacing will also be 0.15 meters. And now we have this longitudinal reinforcement in both directions for both the top and the bottom across the entire surface. Now, if we're also interested in placing reinforcement, maybe we need additional reinforcement where locations such as columns are framing into the slab or walls, we can simply create a new definition type here. And instead of the location type set to the entire surface, we can set this to free rectangular. The reinforcement type might be rebar. We could select whatever here, 15 at 0.15. We also went transverse reinforcement. Same concept here, spacing at 0.15. I could even add in an additional offset here to offset from my number 15 bars in this first definition type. But under this second tab, this is where we can graphically place this reinforcement in certain areas of the surface. So you'll notice here that if I turn on my grid settings, just to provide a little bit additional guidance here, I can then just click on 2 points, which I know is a little bit difficult for you guys to see, but I click on these 2 points maybe over my column and my wall at the center of the slab where I'd like to apply this additional reinforcement. The coordinate points are automatically populated here, and now we're taking into consideration both of these reinforcement definition types. What else has been recently released within RFEM 6 is this new auto function. So if we would prefer the program to optimize the bar size for us based on the required reinforcement from the analysis and design, we can choose the auto function. When we choose this, a dialog box pops up that says what minimum size do we want, what maximum size, and then again, the program will optimize that bar diameter for us. In addition to the auto function for the bar number, we also have the auto function for the spacing. So when we choose the auto function here, we specify the minimum spacing, the maximum spacing, and the increment. And again, the program will optimize this based on our required reinforcement from the analysis. Now, it should be known that you cannot use the auto function for both the bar number as well as a rebar spacing. You kind of need to choose one or the other here, but it also can be applied to the transverse reinforcement. Now, for today, I'm going to totally delete this definition type, and we will just utilize this uniform longitudinal reinforcement throughout the entire surface. Also, this surface definition can be applied to more than one surface. So if I want to use the same reinforcement at every single floor level for my floor slabs, I can easily apply the same definition type to multiple surfaces. This way, if I need to make any modifications, I go back in to edit only one definition type here, which will then affect all of my surfaces. So now that we have this specified here, what I'd like to do is to go to the design configurations. Very similar concept to what we saw with our members. For the ULS design, instead of the members tab, we go to the surfaces tab. Again, just various options for the ULS design specific to our 2D surfaces. Maybe one important topic is we would want to maybe change this, whether we are designing a plate or a flat slab versus a wall element for maximum longitudinal reinforcement. Again, we can create multiple definition types to assign them to our walls versus our floor slabs. So once this information is input, we'll check out the serviceability. This actually is identical to the configurations for our members as well. We're also going to check deflections here for our surfaces. Again, create multiple definition types if you'd like to have maybe different limiting deflection ratios for members versus surfaces. And finally, the deflection tab. So this allows me to specify if this surface is supported at both ends or is it a cantilever. We need to know this information for the limiting deflection ratio. All right, so now that this input information is complete, what we should see here then, if I cancel out of my visibility, is the reinforcement shown graphically for our surface as well. So this is going to be that longitudinal reinforcement at both the top and the bottom shown graphically. If this does seem to get in your way graphically, just go ahead and navigate to the Navigator Display tab here, and up at the very top, we can turn off the types for concrete design. So the final topic here is going to be punching shear. This is also a new feature that we have recently released within RFEM 6 for both the ACI and the CSA standard, is the ability to check punching shear. Well, when we look at this column framing up into this slab, this is probably an area that we would want to carry out that design at this particular node, but we also can check punching shear at wall ends as well. So holding down my control key, I'm going to select both of these nodes here and double click on them. We have an additional checkbox down at the bottom to turn on the punching design, again, specific to that concrete design add-on. And we now get an additional tab here for the ultimate configurations only for punching shear. So we've already visited members and surfaces, but now we have this fourth tab specific to the punching shear design for the CSA standard. Now, it should be known that currently the punching shear is carried out with no reinforcement considered. We do plan to add in the near future the ability to specify the additional shear reinforcement for two-way shear design or punching shear design, but currently all checks are carried out with the unreinforced section. So now that we have specified here this additional checkbox for these two particular nodes, we are ready to visit the concrete design add-on input data within the table here. So canceling out of this visibility mode, let us choose the concrete design here within our drop-down box. And this is only available because, again, I've activated that concrete design back in the base data. Well, under the design situations here, remember I said design situations are always needed to carry out the design within these add-ons, and here they are listed again. So we have our ultimate limit state design situation that we want to tell the program to go ahead and carry out the ultimate limit state type for all of my elements that I plan to design. We also have our serviceability or unfactored load combinations here with this second design situation type, and we want to modify this here to the serviceability limit state. Now you'll also notice within this dropdown we do have the earthquake limit state. So currently we can carry out the reinforcement detailing requirements for seismic according to the CSA standard. So keep that into consideration that it is the detailing only checks right now. Now we continue to move forward with development to do additional seismic checks in the future. If you are interested though for the reinforcement detailing for seismic, you would just simply go back to our load cases and combinations. You can make a copy of our ultimate limit state design situation. We would have a third line here where we can now relate that to the earthquake limit state type. And we also have here the objects to design. Now, by default, the program automatically selects all objects, but you can see that we get some red values over here. And this is just simply because we have not defined reinforcement. So there's no way to carry out the actual design of those elements. Rather, I want to graphically select here the elements that I would like to design where I've already input in the reinforcement. This includes our 4 members for our columns, and I click OK. We also can design the member representative. Now we only have one within the program here, and we might be wondering what's the point of defining here or designing the member representatives versus the individual members. If you want more of an envelope solution of the design considering all 4 of these members, you can design the member representative. The surface, we only have one surface that we have input in reinforcement, number 79. And for our punching shear, we only have 2 particular nodes here that we have also specified to carry out the punching shear design. So now that we have input in all of this information, we're ready to run our calculation. And I do so directly within the table options. And you can see that the program will now cycle through all of my load combinations here for the analysis portion, taken into topics like the eye crack factor. You'll also see here that we rerun the serviceability load combinations, and this all just relates to that effective moment of inertia that we need to recalculate to determine the deflection checks within the concrete design specifically. And finally, we carry out all of the additional ULS and SLS requirements to give us the design check ratios for all of these elements we have considered. Now, before I get into the concrete design, let us back up a step just to view the static analysis that's available within our Navigator results option. So nothing to do with design right now, but you can see here that we're currently looking at the global deformations, and I can cycle through these different load combinations to see the deformation of the structure. But we're also likely interested in topics like the member internal forces. Now, currently, I only have one set of members here for my columns, but we can view the internal forces graphically, such as the axial forces or the shear forces, bending moments. And all of this information is also available in table format as well. If we go to results by member, we can view that information rather than just graphically, but also table format. It's also important to look at the surfaces. So what I want to do here is maybe we'll create a user-defined visibility for only that particular surface that we're designing. And we activate here the surface results, such as the basic internal forces. We have here MX, we have MY, MXY. All of this internal force information is used in the design of this slab within the concrete design add-on. What I want you to take note of is these membrane forces or in-plane forces, NX and Y. So you'll see here that we clearly have some high values for the in-plane forces of this particular slab. Keep this in mind because this topic will certainly change when we get to the building model add-on and we define diaphragms instead. So now that we have quickly covered the output here from the analysis, we want to take a look at the actual design according to the CSA standard. So under the concrete design here within the table, we're just getting a quick overview of maybe where we have some problem areas. But before we address these, which are mainly located in our surface, let us take a look at the design ratios on the members. And I can graphically turn on the design ratios of the members here so that we can see, again, specific to the concrete design add-on. So I'm currently looking at these design ratios tab here for each of the members, and notice that everything is synced up within the table as well as the graphical view, so we can view the design checks for the columns at each floor. And we have for each column the ULS checks and SLS checks. If we wanted to take a look at the design check details for each one of these particular checks, we can access this here within our table. It's called Design Check Details, and this is new within RFEM 6. What this allows us to do is to view the equations line by line, along with the variables, the code references, everything is given here so that we can show you how the program has determined this specific design ratio for this ultimate limit state check. We can add this information to the printout report. These calculations and formulas will update in real time in the printout report if we make any modifications to the model. Additionally, we can use our drop-down box here to switch to a different design check if we'd like to see those formulas listed out here. We can expand out our table if we're interested in seeing some of the analysis information or variables that again go into this design check details. Also new within RFEM 6 that we previously did not have in RFEM 5 is the interaction diagram. So we can activate this here and we get a third tab. And here we will see the interaction, the 3D interaction diagram for our particular column under the applied loading. We can add this as a graphic to our printout report, but we also see the values here in table format. Additionally, we can see exactly which point we fall under within this moment interaction diagram under the applied loading for this particular scenario. So very powerful in the sense of all of the detail output information that we have added in RFEM 6 for the concrete member design. So in addition to the design of the members, we also have here the design ratios on the nodes for our punching shear. So we'll go ahead and turn on the graphical display of this. Maybe we turn off the members, and we can view here in a bit more detail in table format as well as graphically the punching shear. So as mentioned, this is always considering, at least at this point in time, the slab is unreinforced for additional shear reinforcement, but this allows us just to view, okay, is the slab adequate without that shear reinforcement, or do we need to additionally take that into consideration? Looks like we're a little bit overstressed here with the shear design check for punching shear at this particular wall end. And finally, we want to take a look at the design ratios of the surface. So we see this in table format here, and I'll go ahead and turn on the design ratios of the surfaces graphically. Well, a lot of these checks appear to be okay, but we certainly have some issues, especially when we're talking about shear checks at maybe where the column is framing in to the surface. So very high design check ratio here, over 3.0. Well, the slight problem here is that, remember, we have this column framing into the beam here, and it's framing into this slab at this single FE mesh point here, this node shown graphically. And we know in reality, we're going to get better load distribution than what we can show in an FEA program where all loads are coming in at this single mesh point. So this is called a singularity. And this is not unique to RFEM, but all FEA programs deal with singularity. So the question is, what tools do we have in the program to deal with singularities, especially with the concrete design, so that we're not over designing this structure, because in reality, again, we know we're going to get better load distribution. So let us go back to the basic model here, and I'll go ahead and create a user-defined visibility with only this surface. To address singularities, the first thing that we want to do is to double click on this node and to add in what we call a mesh refinement. So currently within the global model, we have a mesh setting of 0.5 meters. Well, a nodal mesh refinement here will allow me to create a new definition type where I can specify, for example, the radius of 1.5 meters, and to refine that FE mesh at 0.1 meters at the interior, and we'll transition to 0.3 meters at the exterior. So once we have this definition type set, we do need to clear out our results. We click OK, and now we see this additional symbol shown here graphically for that FE mesh refinement. So after we have set the FE mesh refinement, there's also an additional element that we want to add here. And this is found under the Navigator Special Objects folder. We see Surface Result Adjustments. So we can right click to create a new definition type. And what this will allow us to do is to actually average out the forces over a set area. So that way we can kind of smooth out those high peak forces. We will specify this one as a rectangular shape with the dimensions set at 0.8 meters by 0.8 meters. I can graphically select this node here right where the column is framing into the slab. And I also want to select the surface that I would like to average out these internal forces. So surface number 79. Now, a very common question is, well, what size do I set this average region or this surface result adjustment to? This is really up to the engineer's discretion. If you set this to something too large, then maybe we're not accurately capturing high internal forces here that really will occur. If you set it to something too small, then maybe we're over designing because we know in reality we're getting better load distribution. So for today's example, just a completely arbitrary value here of 0.8 by 0.8 meters. When we click OK, what we see here now is a graphical symbol as well for that surface result adjustment. Well, what's nice is that if I hold down my control key to select both the surface result adjustment as well as the FE mesh refinement, I hold down my control key once again, we can drag and drop this and place it at different areas along this same slab where maybe a singularity is an issue. So at the wall ends, for example, or reentrant corners, or where we have openings like this with, again, sharp corners, these all may be singularity issues within the program that we can apply these two additional elements to help address the singularity. So once we have applied the surface result adjustment, the FE mesh refinement, we're going to rerun the calculation here within the concrete design add-on. So because we made modifications to the mesh directly within the RFEM model, we do have to rerun all of the load combinations because inevitably we're going to get slightly different load distribution when we make modifications to those mesh settings. We'll also, yet again, cycle back through the serviceability load combinations here for that effective moment of inertia and deflections. And finally, we'll apply the code equations from the CSA standard. So now that we have finished this calculation, let us jump to the design ratios on the surface. And I just want to point out that now a lot of these design ratios are either below 1. We have one small issue here that's slightly above 1.0 with the serviceability crack control. But again, we've kind of smoothed out those high peak forces so we get much better results in addressing those singularities. The same concept is also applied here to the design ratios on the nodes. We can see that this value also dropped down as well. The final thing just to show you within the graphical view is that currently we've been viewing everything based on the design check ratios, but keep in mind that we also have the reinforcement view here. And we can view the required reinforcement based on the analysis here in the longitudinal directions for both the top and the bottom. We can also view the provided reinforcement. So this is my number 15 bars at 0.15 meter spacing. This is uniform, so that's why we're seeing just one solid color here. And then we have the not covered reinforcement. This is just the program simply looking at the required reinforcement, comparing it to the provided reinforcement. And if we are not meeting the criteria set forth by the analysis and design, we would see additional areas here in the slab where we would want to add more reinforcement, but it looks like it's adequate here for our example today. Okay, so now that we have a general understanding here of the concrete design add-on, I am going to jump to an already saved model where we can touch on the building model. So I'm going to revisit the base data here. And by the way, this structure in the background is the exact same model that we have just been working with. The only change that I made here under the add-ons is I have now activated the building model. So what we're trying to do here is that RFEM is a general FEA program, meaning that any structure is possible to analyze and design. We want to implement more building specific features into this general FEA program for, again, those building specific projects. So when we activate this add-on and we click OK, at first glance, it seems like not much is different here with our input data, but we now have an additional folder here called building model, where I can right click to create a new building story for my structure. Now, by default, this first story is created, but I do need to modify what's the bottom of the story versus what's the top of the story. And I can do so by simply clicking on these 2 points here at the base of the structure, and we can see that the height is modified here to 3 meters. Additionally, we'll see all of the input information specific to this story that we have just defined based on all of the elements that are tied to it, including the walls, the floor slab, members, and whatever else it may be. We also have the floor modeling drop-down option here to define a diaphragm. Now, if I leave this as empty, we're simply going to continue utilizing the concrete surfaces that we already have modeled within our structure. Alternatively, we have the load transfer only, so you can think of this as a flexible diaphragm where we are going to distribute the loads based on the tributary area of all elements that lie within this story. And then finally, we have the rigid diaphragm, and that's what we're going to utilize for today. Essentially, we are going to consider each one of these floor slabs with a infinitely high stiffness in the in-plane direction, and we actually extract out each one of these floor slabs to run a separate calculation with the bending moments only. So I want to continue defining these additional stories, and I can do so with this button here in the lower left-hand corner. And the program assumes that I have the same story height at each level, but of course we can make modifications to that if we need to. When I click OK, what you will notice now is that each of these stories is now shown graphically with the dimensions and the labels shown here. You'll also see, if I go into wireframe view, a very different view of each one of these floor slabs. And we notice all of these red lines shown to us here. Well, these red lines are just representing graphically that rigid diaphragm. Essentially, we are going to tie together every single FE mesh point at this elevation with that rigid diaphragm constraint conditions. Additionally, if we take a look at that concrete surface that we've defined at this level and we double click on it, the program has automatically modified the stiffness type here to a floor slab rigid diaphragm. Now we can still carry out the design according to the concrete design add-on with the checkboxes shown here. Everything is fully linked there, but you should take notice here that the stiffness type is no longer standard, but now it's of the type rigid diaphragm. If these rigid links seem to somewhat get in your way graphically, you can always turn them off with the second tab here in our navigator, where we can turn off the rigid links under the special objects. Additionally, you'll notice a couple balls here shown in the center of these floor elements. The first is just going to be the center of mass, but also the smaller one here, if we double click, this is going to show us our floor set. With the floor set, this is going to include all of the connected surfaces, including all of those shear walls, the connected members. It will show us information specific to that particular story. So once I have defined the stories, I'm going to go back to the navigator here to define shear walls. So I'm going to turn this into a rendered view. And with the shear wall definition, I right click to create a new shear wall type. I will immediately select here a set of shear walls. So we'll choose these ones just arbitrarily over on the left-hand side. So 4 shear walls in the vertical direction. You can see those surfaces are generated here. What the program will do in my output is to create what we call a result beam. It's going to simplify the internal forces for these 2D surfaces and represent it as a member element. So this will make a little bit more sense once we get into the result output here from our building model add-on. But now that I have created this first set of shear walls, notice these are shown here, the cross section, I'm going to create a second set as well. And the shear wall definition does not necessarily need to be in a single plane. So for example, notice that I'm choosing the shear walls at the corner of my structure here that have a 90-degree bend in them. So I choose all 8 of these segments, I click OK, and now you'll see here the shear wall is actually represented by these 2 segments at a 90-degree angle. Now we can take the result beam from this first set of shear walls and actually design the reinforcement in the concrete design add-on as a typical member. And I will show you that shortly with the spandrels. But for the shear walls here that are at a 90-degree angle, it's not quite ready in development that we can also design the reinforcement. We can only consider one single plane right now, but this is still going to be helpful in the analysis output in just a minute. So once this information is input for our shear walls, we want to do the exact same thing for our spandrels. And actually what you'll notice is that I've already taken the liberty here to define a couple of those spandrel definitions. We'll start here with the first spandrel at the front of the structure. It's located above this larger opening. I also created a second spandrel definition by simply selecting these two surfaces here over the larger opening. But notice that I selected two surfaces here. So if you have a spandrel that spans over a particular story or floor slab, that's no problem. Ultimately, similar to the shear walls, we're going to create that result beam to represent this 2D surface as a single 1D member. So just a simple example here for our spandrel definition. So now that we have this information defined here within the model, I'm just going to quickly run one of the load combinations, such as load combination number 4. So we'll go ahead and start the calculation for this. Notice that the program will actually create a few calculations here because we need to extract out that rigid diaphragm for the separate analysis, separate from the lateral system here. So now that the calculation here is complete, let us turn into a wireframe view. The very first thing I want you to notice with the building model add-on is this first option up at the top. So we have 3 options now. We can view the main option, which is essentially going to be currently the deformations for all of our wall elements and member elements, anything that is not a part of that rigid diaphragm. So we can more or less think of this as the lateral system. We also can toggle here to the floors only. So now we can see the results for only these 2D rigid diaphragm surfaces. And finally, we have the combination here for all elements considered together. So jumping to the floor elements only, not looking at the global deformations, but rather turning on the surface internal forces. Again, we have MX and MY forces that are going to be used for the concrete design, but a very big difference than what we saw before is if you take a look at NX and NY, these values are now 0. And again, that's because we have that infinite stiffness in the in-plane direction of our surfaces that have been redefined with the rigid diaphragm definition type. Jumping now to the additional elements here other than our floor slabs, I wanted to point out the member internal forces here. And I want to show you what we call the result beams. So we'll go ahead and activate here under our members. The members by type only are result beams. Let me go ahead and turn those on here. So what you will see with the result beam view is, again, the program is summing up the internal forces for these 2D surfaces and representing it as a single 1D member element. So now we can view information such as the shear forces or the bending moments for these shear walls, axial forces, whatever it may be. And also, remember we had defined those shear walls at the 90-degree angle here at the corner. We still have a result beam that is summing up the internal forces for both of those segments, regardless if they're in the same plane or not. Same concept here for our spandrels. We're summing up the internal forces for this single surface over on the left, but both surfaces are summed up here, represented by a one-dimensional member. We can view information like bending moments. So now with this information, we can take these result beams into the concrete design add-on and to actually carry out the design of, let's say, this spandrel as a single 1D member. So if we cancel out the visibility mode here, and I'll turn this into wireframe view, I'll create only a visibility of this single spandrel. I double click here and we can see that this is now represented as a result beam. So this is more or less overlaid on top of that 2D surface. But we have all of the design properties shown to us here where we can specify for this spandrel, the cover is given. The shear reinforcement can also be defined. And just one thing to point out here that may be applicable for topics like shear walls and possibly even spandrels is that in the next week or two, we will also release the ability to define cross ties that will be taken into consideration here with the shear reinforcement as well as the design. So more or less those cross ties can be applied to the longitudinal reinforcement. So keep an eye out for that within the next week or two. Longitudinal reinforcement can also be defined. So you can see here that I specified 4 bars in the corners, but I also utilize the rebar type line here to specify 8 additional bars at the top, and we also have 8 additional bars at the bottom. So more or less designing this spandrel now as a deep beam. And finally, under the concrete design add-on, what we would want to do here is now that we have input in the reinforcement for this result beam, we will also select it here under the objects to design. And just to quickly show you exactly what the calculation looks like in the last couple minutes here, we'll go ahead and cycle through these load combinations. Notice that it will take just a minute or so longer simply because we have those rigid diaphragm definition types that we need to extract out and do the separate calculation for those 2D elements. Again, running back through the serviceability calculations here for that effective moment of inertia for all of the relevant objects that we have designed, and finally applying the CSA load combinations with the output as we see here with the progress bar. So once this information is complete, everything that we have seen up until this point is the same. The only thing that I wanted to point out here is that we want to jump to the design ratios on the members, and we see that this member here is designed as we would any other particular member within the model. So we can view the design check details for this result beam here. But overall, just treating this spandrel like a deep beam or a simplified beam as well to carry out the reinforcement design according to the CSA standard. Okay, so we will jump back to the PowerPoint here to wrap up today's webinar. I know this is quite a bit of information. This webinar is recorded. It will be placed on our website on the same webpage that you use to register for the webinar as well. You can currently download this model that I used in the example, and feel free to access the 90-day trial of RFEM 6. So this trial is full capability for 3 months, and it includes all of the add-ons such as concrete design add-on, the building model add-on, and anything else that you wish to test. Now, if you have any questions about today's presentation or any of our products, feel free to contact us at our USA Philadelphia office. Our phone number is shown here at the bottom of the screen, 267-702-2815, and our email is info-us@delubal.com. So we will have many more upcoming webinars. We hold these approximately every month. You can register at delubal.com under support and learning and webinars. As most of you know, I will send out a reminder email about a week before these take place, so you can keep an eye out to register through the email directly. We will also be issuing PDH certificates. These will be automatically emailed to all participants who were here for the full presentation. So it is a requirement from the states that we are pre-approved providers for PDH, that attendees are here for the full duration, the 60 minutes of the webinar, in order to receive that PDH. If you did watch with a colleague or you watched in a conference type setting and you yourself did not register for this GoToWebinar, you will need to request that PDH at the email address shown here, info-us@delubal.com. So again, if you yourself did not register for the webinar with your own name and your own email, go ahead and send us an email here to request it. Let us know who you watched it with, and of course, be sure that you are here for the full duration of the presentation. And with that said, I want to thank everyone for attending today's presentation. And as always, we hope to see you at the next one. Thank you.